In this section, we'll look at a number of situations that involve the use of determinants. The first is in solving systems of equations, and the method we're going to use here is called Cramer's rule. Cramer's rule allows us to solve some systems that we wouldn't be able to conveniently solve using the methods that we've talked about up to this point. Cramer's rule works like this. It's a rather simple kind of looking situation once we analyze it overall. Suppose we have these two equations and two unknowns. We're going to define a few determinants here, and then it's just a matter of writing some fractions involving those determinants to get at the answers to the system of equations. Well, let's define D as the determinant of the coefficient matrix. Now, the coefficient matrix is a matrix composed of the coefficients. It would be the matrix of 4, 3, negative 2, negative 5. So D is the determinant of that coefficient matrix. Now, a couple of other determinants are necessary here. We'll define D subscript x as the determinant of a matrix that is formed by taking the coefficients of x and replacing them with the constants. Imagine the 10, 11 being in these positions, and then negative 2, negative 5. So 10, 11, negative 2, negative 5. And D sub y is the determinant of a matrix which is formed by taking the coefficient matrix and replacing the coefficients of the y's with the constant. So it would be 4, 3, then 10, 11, like this. All right, now we'll make the calculation for these determinants in just a minute, but let me tell you how the answers are going to occur. It's very simple. We just take these values and we make fractions out of them. X turns out to be the D sub x determinant, you see, over D. And y is D sub y over D. And that's all there is to it. All right, back over here, let's calculate the determinants. Here, this determinant is, well, let's see, 4 times negative 5 is negative 20. And then minus 3 times negative 2, negative 6. So this becomes plus 6, negative 20 plus 6 is negative 14. And then 10 times negative 5 is negative 50. Then minus the product along this diagonal is 11 times negative 2 is negative 22. So this becomes plus 22. Negative 50 plus 22 is negative 28. Looks like I'm getting a little jammed with this other part. Let me just do this. There we go. And let's see, this D sub y is 4 times 11, 44, minus 3 times 10, 30. 44 minus 30 is 14. All right, now let's make those fractions. Now notice D is negative 14, D sub x is negative 28, and D sub y is 14. So x then is D sub x over D. D sub x is negative 28. D is negative 14. So x then is 2. And y is, let's see, D sub y over D. D sub y is 14. And D, negative 14. So y is negative 1. And that's just all there is to it. Now there's one catch in using Cramer's rule. We would just universally use Cramer's rule all the time when we have systems of equations if it weren't for the fact that sometimes a determinant is 0. That is, you know that determinant numbers can be positive, negative, or 0. Well, if the D involved in these fractions turns out to be 0, then we would have an undefined fraction here, and therefore we couldn't use this method for solving systems of equations. Let's go through it again using a more complicated system. Here we have a system of 3 equations and 3 unknowns. Now the D determinant, the determinant of the coefficient matrix, 4, 2, 8, 4, 2, 8, negative 2, 2, negative 5, negative 2, 2, negative 5, 3, 5, negative 2, 3, 5, negative 2. And we go through the process using the techniques that we learned before about calculating determinant. I'll go ahead and make the calculation here with this one, but I'm pretty confident that we can do this on the others, and we're not going to bother with the calculation, the nuts and bolts of the calculation in the future. Now I'm going across the top here. It's 4 times its cofactor, and remember the cofactor has associated with it a sign, and the sign pattern here is plus minus plus, so let's keep that in mind. So it's 4 times, let's see, the cofactor is simply the determinant of, take out row and column, 2, negative 5, 5, negative 2. That's this. And then it's minus 2 times, now the sign associated with that position is negative, you see, and then the determinant is, take out row and column, 2, 8, 5, negative 2. So that's how I got this. And then 3 times, now the sign is plus minus plus, so we don't have to worry about that. Take out row and column, and we have 282, negative 5. 282, negative 5. And then making the calculation, it's 4 times, this becomes 21, and the minus minus becomes plus. 2 times, this determinant is negative 44. 3 times, this determinant is negative 26. When the smoke clears here, we find D to be negative 82. Now, the calculation of D is the most important of all of the calculations in the problem because D occurs in the denominator of all of those fractions that we're going to form. So if we miss the calculation of D, then we naturally will miss all of the values for x, y, and z in a problem like this. So this is very important. If we miss d sub x, d sub y, or d subscript z, then we'll only miss one of those values you see in our list of solutions. Well, at any rate, d sub x turns out to be the coefficient matrix except with the replacement of the coefficients of x, which were along this column, with the constants. So slide back over here and let's make sure we understand that. If we took the coefficient matrix and we took out these entries, the coefficients of x's, and replaced them with negative 2, 16, 4 in this position, and then write down all the entries as we see them here, then we would have this d sub x matrix. And now we want the determinant of that matrix. It turns out to be negative 410. The d sub y matrix turns out to be, well, take the values that were in the coefficient matrix as the coefficients of y, take those out and replace them with the constants, and here we go with this column. And then this same column will appear in d sub z as the values that were the coefficients of z. So that's how these are all formed. D sub y turns out to be negative 656, and d sub z turns out to be 164. By Cramer's rule, then, the value of x is d sub x over d, y is d sub y over d, z is d sub z over d. And the d sub x we found to be negative 410, d is negative 82. So x is 5. Then d sub y over d sub y was negative 656, d is negative 82. The fraction becomes 8. D sub z is 164, d was negative 82, so z turns out to be negative 2. The ordered triplet that solves the system of equations is 5, 8, negative 2. Now, because we go through so much calculation in problems like this, it would be valuable to check this answer, this group of x, y, z that represents the solution for the system of equations. And really, if you don't, you should, to validate this as a correct solution, you should check these answers with all equations. But realistically, if you just check these as solutions to one of the equations, then it's probably the case that these will be solutions to the entire system. Another situation where we can use determinants is to find the area of a triangle given the vertices of the triangle. Suppose, for example, we're given vertices of 1, 3, 3, 2, 2, 0, and we want the area of this triangle. Well, I've drawn the triangle here, and just think about the difficulty of finding the area. We have an area formula. Area is 1/2 base times height. But gee, in this circumstance, we would need to identify a base and a height, and the best of all worlds would be for us to have a right angle here to determine whether or not we have a right angle, and we do here, by the way. But to determine that, we would have to find the slope of the line containing those 2 points, the slope of the line containing these 2 points, and determine that those slopes are negative reciprocals of one another. Okay, that's done. Now we think of this side maybe as the base, and this side is the height. Well, to find that distance, we would have to use the distance formula, and then the distance formula here again. It's a pretty involved process. Now, using determinants, though, the calculation is particularly easy. It turns out that given the vertices of 3 points, we can determine the area of the triangle having these vertices with this little calculation. It's plus or minus 1/2 times this determinant. Now, the determinant, notice, is composed of items from the vertices. The first 2 items in these 2 columns are just xy pairs from the vertices, and the last column is just a bunch of 1s. Okay, so 2, 0 from here, 1, 3 from here, 3, 2 from here. Now, the plus or minus is just in here to make sure that we get a positive value. We could just as easily say absolute value of this whole thing, but then that would kind of conflict with this absolute value looking symbolism right here. But so plus or minus is just to accomplish a sign change if we need it. Now, let's go through the process of making the calculation for the area of the triangle. I'm going through, let's see, I think I went across the top here because of the involvement of the 0. So it was 2 times its cofactor, and that cofactor is the 3211. You see, and then 0, and who cares what else is there, and then 1 times its cofactor. Take these out and we have 1332. So that's how I got those. And now this is 2 times 3 minus 2 is 1, and over here it's 1 times 2 minus 9 is negative 7. So now we have 2 with negative 7. Gee, that's negative 5. Half of negative 5 is negative 5 over 2. So we'll apply the minus sign here in this sign pattern to give us a positive value for the area. It's 5 over 2. So that's all there is to it. Rather simple little calculation. Now, as a related matter, another use for determinants is to find out whether or not 3 points are collinear. Now, it doesn't maybe seem on the surface to be related, but if 3 points are not collinear, then a triangle could be formed with them, and that triangle would have an area. If the 3 points are collinear, then the triangle that's sort of formed with those 3 would have an area which would be 0. Now, let me make sure we understand that idea. Suppose we have 3 points, and if they are not collinear, kind of like this, then a triangle could be formed and that triangle has an area. On the other hand, if the points are collinear, then something like this, then from here to here, and now the segment from this point to that one would be right on top of these other 2, you see. And so it's like the triangle has been squished down into one line, and so it would have no area. And so we use a part of that area formula for the calculation of whether or not the points are collinear. Now let me show you what part we need to use. Let's rock back over here a little bit. We have, in this calculation for area, it was 1/2 of this determinant. And this is kind of the base times height part of the calculation for the area of a triangle, if we're kind of referring it back to previous knowledge. But if this value turns out to be 0, then of course the area would be 0. And if this calculation, if this determinant is not 0, then this area will not be 0. So it's this part of the calculation that we're going to use. So let's do that. If we want to determine whether or not the points given by these coordinates are collinear, then we do this. We just go into that part of that area formula that we need. Now the -2, -2, 1, 1, and 7, 5 come from the coordinates of the points, and then the 1s along this column. So we just make the calculation. I think what I did here is I decided to go down this column. So I just said 1 times its cofactor, take out column and row, we have 1715, 1715. And then for this one, it is plus this 1, and then the sign associated with that 1, though, is negative. Remember that sign pattern, plus, minus, plus. So it's minus. The determinant is, take out row and column, -2, -2 on top, and then 7, 5 on the bottom. And then this 1 times, take out row and column, -2, -2, 1, 1. All right, and then after making the calculations, we find that the value of this determinant is -6. If this value is not 0, then it means that the points are not collinear. Here's another problem where we're going to use the matrix format for a solution. The problem is one that we've seen before. It says write an equation of the line containing these 2 points. Now, when we had a problem like this in the past, you know, we had to go to a special form of a linear equation, and that was the point-slope form. And let me just show you by contrast what that method looked like, and then we'll come back and work it using a matrix. So if we were given a couple of points and we want to write an equation, we start with this point-slope form of the slope formula. That's kind of the way we thought about it before. And in this form, we are requested to give the coordinates of a point and information about the slope? Well, we can produce the coordinates of a point because we have the coordinates of 2 points. Now I'm using here the coordinates of the simpler point, the 2, 1. So the 2 goes in place of x, the 1 goes in place of y. But what about the slope? Well, we have to go to the side and make the calculation for the slope. So we slide over here, and using these 2 points and the slope formula, we plug in, we find the slope to be negative 1/3. We bring that information back over here, we pop in the negative 1/3, and let's see, negative 1/3 times these 2 produces fractions. And then to clear the fractions, we multiply through by the common denominator 3. Now, I've done that here to clear the fractions, and now we move all the terms to one side and simplify, and finally we have the equation. Well, let's look at it using the matrix idea. Now, we're setting up the same kind of arrangement that we set up in the last problem. Now, generally the arrangement is like this. We're thinking about xy pairs in these 3 positions, and we have a column of 1s over here as we saw earlier. Now, notice that in this arrangement we have a subscripted xy pair here and another subscripted xy pair. And this is the key to tell us that we're using the coordinates of the given points for these 2. All right, and all we do is plug in and then simplify using the information we know about how to go into kind of a more of an expression kind of pattern with this. But just understand that here's what we're doing. Here's how this relates to the previous problem. Remember, we were trying to decide whether or not 3 points were collinear. And we said that if this determinant turns out to be equal to 0, then we have collinear points. If this determinant turns out to be other than 0, then the points are not collinear. Well, we're making this determinant equal to 0. So we're saying we're going to produce a situation where those points are collinear, and we have one of those points is a general point xy. So what we're really doing here is we're producing information about all the points in the world that are collinear with those 2, you see, and all the general points xy that are collinear with these 2. And that's kind of a different way of looking at the nature of an equation, the equation of a line. Anyway, here's how it works. I've plugged in the 2 points here, and then we go through the process of sort of evaluation. Now I'm going across the top with this. Oh wait, let's stay down here. Come back over here. We're thinking about x times, let's see, take out column and row, the determinant 3, 1, 1, 1. And then I'm going across. Then y times, take out column and row, negative 4, 2, 1, 1. And then 1, and then take out column and row, the determinant negative 4, 2, 3, 1. So that's what I have over here. So I have all of this, and then it's equal to 0. And then we just go through the little evaluation process. This is 3 minus 1, which is 2 times x, 2x. And then here we have negative 4 minus 2. That's negative 6. But this minus sign makes this plus 6y. And then here we have negative 4 minus 6, that's negative 10. So negative 10. Now I'm noticing here that all of these are even, and therefore I'll go through and divide by 2 to simplify things a little bit. And now we have the equation of the line containing those 2 given points. Another area where matrices are used rather extensively is in the area of cryptography. Cryptography is the matter of sending and receiving coded messages, and this was really important back in the Second World War when military leaders would send messages to one another. And there was this, kind of a life-threatening cat and mouse game going on where one side was intercepting messages from the other, and the attempts were made to decode the messages, and it was important to write a code that couldn't be broken and all that kind of thing. Well, the interest now is more probably on the internet than anywhere else, where we want to send secure information about credit cards and such things. Well, let's talk about a strategy for coding and decoding messages. It turns out that we can take a message as simple as, oh, please send money, and we can assign a number to each of the letters. Now, we can do that just by going down the alphabet. We can say, let's let 0 stand for a space, and 1 corresponds to A, 2 corresponds with B, 3 corresponds with C, and so on. 26 corresponds with Z. We can even have correspondences of numbers with certain digits, you see, numeric digits. Well, at any rate, then this message would correspond to a string of numbers that would be 16, 12, 5, 1, 19, 5, and so on. Now, if you just sent this message and someone intercepted it and wanted to decode it, it would be pretty easy because the correspondence is right with the letters of the alphabet. But here's what we can do using matrices to make this a very secure kind of message. We kind of send the message into a matrix filter, we could think about it like that, into a matrix filter, and then on the other end we send it back through the undo filter, kind of like this. Suppose I take this string of numbers and I divide them into groups of some number. Now the number in the group could be 3 or 4 or 5 or whatever you decide. I'm going to think about groups of 3. So these are in a group of 3, those are in a group of 3, here's a group of 3, here's a group of 3, and so on, all the way to the end. Now I see here that I only have 2, so I'll just put a 0 in here to hold that place, kind of like a space, you see. Okay, now what I'll do is I'll take the groups of 3 and think of them as a matrix, a little 1 by 3 matrix, 1 row, 3 columns, okay? And then I will decide on a matrix for the code. Now I've chosen this matrix for the code for no apparent reason. The important thing in choosing a matrix for the code is this, that if you're dividing into groups of 3 for this purpose, then you need to have a matrix for the code that is a 3 by 3 matrix. And that matrix has to be invertible. That is, it has to have an inverse, because that's going to be the technique for deciphering the message. At any rate, I've chosen this 3 by 3 matrix. All right, now we know that if we multiply these two, you know, this is a 1 by 3, this is a 3 by 3, so the answer when we multiply will be a 1 by 3 matrix. And when we multiply, we get this. Now, here is the code corresponding with the 16, 12, 5. And then you take the next group of 3 and send it through this filter, this matrix filter. So just multiply times this same 3 by 3 matrix, and we get these numbers. Now the really neat thing about a code such as this is that a single letter can take on different values at different points within the message. For example, you know, we started out with P-L-E-A-S-E. Now notice that E is the third letter here. It's the third letter in this group of 3 as well. So here we have a 5 here and a 5 here that both stand for 3. But look at the code. In the coded part, we have a 9 here and a negative 13. So, and these are just the positions for E, you see. So that's the neat thing about this. Well, this seems like a lengthy process for such a simple message, and it is pretty lengthy if we're going to go through this using paper and pencil. But the calculator can help us a great deal with this. Let's call this matrix A, and let's call this matrix B, and send some of these through the filter using the graphing calculator. Now, what we're going to do is we've already done the first 2 groups of 3. Let's go through another couple of groups of 3 and see how that would work. Now, this is A, and that's B, and we just have to change B as we go along. I'm pressing the matrix button here and cursoring to the right to edit. As I press enter with the icon on matrix A, we notice that I've already entered the entries that are in our matrix, our 3 by 3 matrix that we had on the board moments ago that will be used to encode our message. Now, second quit will put us on the main menu. Pressing matrix puts us back into the matrix menu. Now what I'd like to do is edit matrix B. So I'll cursor down to it and press enter. And the matrix we're looking for has 1 row and 3 columns. So I'll press 1, enter, 3, enter, and now I'll enter the 3 items that are in the message that I want to encode. And the 3 items are 0, 19, and 5. So I'll press 0, enter, 19, enter, 5, enter. And back to the main menu with second quit. I want to multiply B times A. Now remember, it's B times A and not A times B. We would get a different result trying to do that. So I'll press matrix and then cursor down to B, press enter, and here B comes up. Now I want to multiply B times A, and when we did this matrix multiplication before, we pressed a times sign, but it really isn't necessary to do that. If I simply press matrix and press enter here, I am entering matrix A. So B times A, and then press enter, we get the result. Negative 42, negative 47, negative 14. And we would record this, this information. Then I would go back to matrix and cursor over to edit matrix B to encode or to put into the calculator new information about matrix B. I don't need to change matrix A, you see. All right, it is still a 1 by 3 matrix, and this time the entries are 14, 4, and 0. So 14, enter, 4, enter, 0, enter. Second quit goes back to the main menu. Again, I want to multiply B times A. Now the shortcut to do that would be to press second and then enter, and it will give back the operation that was on board before. And now I press enter again, and I get, let's see, 44, 16, 10. All right, so I would register that. And so forth for the remaining entries in the cryptic message. So using the calculator, we can code all of these groups of 3. Now here are the correspondences for the other groups of 3. We saw the first 2 groups of 3 before, but this group of 3 corresponds with these coded numbers, and this group of 3 with these coded numbers, and so on. And we see how to do that with the graphing calculator. Well, then we take all these coded numbers and just write them in a string. So we have the string of 4369 from over here from before, then negative 32, negative 45, negative 13 from over here, then negative 42, negative 47, negative 14 from up here, and then the rest of them just follow along. So this is the message that is sent, all right? And we don't care if it's intercepted because it's in code. All right, then once these numbers are received on the other end, that is by the receiver wants to get this information and decode it, here's what they have to do. They have to divide these into groups of 3, you see, and then send it through the undo filter. Now notice, and the rest of them, groups of 3. All right, so now the undo filter, the decoding filter, is just the inverse of the matrix A. So we would take these groups of 3, these coded numbers in groups of 3, and multiply times A inverse. You see, and then we'll get back the numbers that we started with in this whole process. Let's just take a brief look at the graphing calculator, at just the button sequence necessary for multiplying groups of 3 times A inverse. Let's just do a couple of these. Pressing matrix and cursoring to the right for editing purposes. I know that A is already on board, so I'll cursor down to B, press enter. And now I'd like to enter a 1 by 3 matrix, so I'll just press enter, enter. Now the items I want to enter here are negative 42, enter, negative 47, enter, and negative 14. Now you recognize this as just being the reverse process of what we did earlier. Well, let's see, second quit will give us the main menu, and now we'd like to multiply B times the inverse of A. So pressing matrix and cursoring down to B, I'll press enter. B shows up on the main menu. Now we want to multiply times the inverse of A, so pressing matrix and then enter right away because the icon is already on matrix A. I'm just about ready to multiply, but I want to multiply by the inverse of A, so I'll press X inverse and now enter. 0, 19, 5. So the decoded message for those encoded 3 numbers would be 0, 19, 5, as we expected, because this is the encoded. These are the 3 numbers that we encoded just a little bit earlier, and now we're just decoding the same ones. Well, let's go back to matrix and go over. And the process would work like this. We would go down to B, and now we would enter another 3 numbers that we want to decode, and those 3 numbers would be 44, 16, 10. So 44, enter, 16, enter, 10, enter. Second quit to the main menu. Then second and enter will give us back the previous operation. Enter again tells us that our decoded information is 14, 4, and 0. Once the complete coded message has been decoded, then we go back through this correspondence with the alphabet. The 16, 12, 5 grouping becomes PLE, and then the 1, 19, 5 is ASE, and then the 0, 19, 5 is space SE. And then it's a matter of stringing these out, putting the spaces in the appropriate places, and we have our decoded secret message.